Hello everyone, welcome to the first video of this series in which we will build neural networks entirely from scratch. So I already have a machine learning teach by doing playlist on YouTube which has 28 videos now, and it covers a lot of details about the types of ML models, classification, regression, introduction to neural networks, etc. While I was making further videos in this particular series, I realized that there has to be a separate series which teaches students all about neural networks completely from the very basics. And that's why I decided to start this series. In this series, we'll be starting completely from scratch. We'll be starting with neurons, then we'll be moving to layers, then we will be moving to activation functions, loss function, optimization, every single thing will be done right from scratch. There is no prerequisite needed to follow this particular series, and all the videos will be uploaded for free on YouTube. My name is Dr. Raj Dandekar, and I have a PhD in machine learning from the Massachusetts Institute of Technology, or MIT. The reason I was motivated to make a series is that I noticed that a number of students, when they transition to neural networks, what they do is that they are just loading packages these days. So let me show you what I mean. There is a very famous library called TensorFlow, using which you can create neural network models very easily in Python. For example, here is the simple neural network code which you can write using the TensorFlow library. Here you can see you can chain different layers together and you can directly use the model.fit function. And I can see that so many students are running this and getting results. But when I ask students, how do these things exactly work? Why do you choose the Adam optimizer? Why do you choose this cross entropy loss? How can you vary the step size? Do you need a regularization somewhere? Do you need to chain different optimizers? Why is this architecture working? Why is it not working? Should we use a mini batch gradient descent, or should we do it over the entire batch? Why or why not? Then how should we optimize the hyperparameters? How should we use the validation set, training set? All of these questions, when I ask students, they are very confused because they don't know how all these commands work right from the very basics. And that is one of the main purposes which motivated me to make this series, because I want to show exactly from scratch how simple it is to build a neural network. So we don't have to think of a neural network as a rocket science or something which is just very complicated, but it somehow works. It's a piece of beautiful mathematics which, if you understand, you'll really be comfortable. Another problem which I noticed with students is with respect to the matrix dimensions. Whenever if you run codes like these, and if you get a bug or if you get an error, and if that error lies in dimensions, it becomes very hard for students to debug that error because they have never written the matrix multiplications which a layer has or which a unit has on a piece of paper, and that's why they find it very hard to debug where the error is coming from. If you truly want to master machine learning, you really need to understand neural networks from scratch. So, if you want, let's say, to solve the handwritten digit classification problem, let me show you this image data set. So, this is the handwritten digit classification problem where the data set looks something like this, and you have to build a neural network which, if given a new number, it classifies what that number is from 0 to 9. That's the problem. So if a student is given this problem, he or she will just search on GitHub that handwritten digit GitHub neural network, and many GitHub repositories will show up. In fact, GitHub repositories will directly give you the code file for this. So here is the TensorFlow implementation of this MNIST problem, and as I mentioned before, it TensorFlow directly gives function out of the box. So you can create the convolutional neural network by just chaining different layers together, and you can run this optimizer, and you can get the results. You can even add these projects on your resume. But if an interviewer asks you what's really going on underneath the hood or how can you optimize it, Or if you are stuck with a new problem, if you solve this MNIST problem, but if I give you a new problem which is more complex, you will be stuck doing it because you don't know the basics behind how this code is written. What does it really mean when we chain these different layers together? How does back propagation really work? And that's why it's very essential for you to know these things. Then I started looking for, are the series like these created on YouTube, and I saw that Andre Karpathy, who I really respect and whose videos I follow a lot, he has one video on introduction to neural network. But even I found it a bit complex to start with. It's a 2 hour video, but it really does not start from the very basics the way I would have liked it to. That is the reason I have embarked on this journey. One more thing to note is that throughout this journey, I'll be following the structure which is outlined in this PDF, which I'm just going to share right now. Okay, so I'm going to follow these table of contents: introducing neural networks, coding our first neuron, coding layers, coding the activation function, then introducing optimization, gradients, backpropagation, training, testing, validation data, L1, L2 regularization, dropout, and then we will take examples, real life examples, and run this entire code right from scratch. So, as you can see, I'm planning to make this series fairly detailed. Uh, Here, I must acknowledge the authors Harrison Kinsley and Daniel, who wrote this particular book and who have organized it into these sections. And I'm going to follow this to make the videos. So, in the first lecture today, I am going to start with coding our first neuron and adding layers. And I'm going to code right from scratch in Python, and I'm going to show you every single thing. Make sure that when you're following with me, please replicate the codes in Python. I'm going to share the code file also in the video description. And I'll implement a whiteboard approach, something like this, along with the Jupyter notebook approach, so that you really understand. One of my main goals also is for you to not get intimidated with matrices and matrix multiplication. So I'm going to explain all that maths in detail. Some of you might find these as very introductory, but later it might get complex. I'm deliberately starting from the very basics, so even those who have learned neural networks can use these lectures to brush up your knowledge. So let's get started with today's lecture. Today we have three agenda. First we have to code. First we have to code a neuron from scratch. Then we have to code a layer of neurons from scratch, and then we have to look at how to use NumPy to basically simplify the coding. So let us get started with the first part, which is coding a neuron. A neuron is basically a unit which takes inputs, and there is a weight associated with each input, and it also has a bias term. So this particular neuron, which has been shown over here, has three inputs: x1, x2, x3. The weights associated with these inputs are w1, w2, w3, and the bias is b. What the neuron does is that it does a summation of these weights and the inputs and then adds the bias term. So x1 w1 plus x2 w2 plus x3 w3 plus b. There is also an activation function involved, but we'll come to that later. Today, I just want to start with this basic summation operation which the neuron implements. And now we want to implement this in Python. So let's see how to do that. So this is building neural networks from scratch, part 1, coding neurons and layers. I'll be sharing this notebook in the video description, so don't worry about it. Okay, so the first part of this video is coding our first neuron based on what we just saw here. Okay, so the way we are going to represent inputs and weights initially is in the form of lists. A list is just a collection of numbers. So here I have three inputs: x1, x2, and x3, and I represent it in the format of a list where x1 is 1, x2 is 2, and x3 is 3. Similarly, when I look at the weights, I also represent the weights in the format of another list, and that has three elements: w1, w2, and w3. W1 is zero point 0.2, W2 is zero point 0.8, and W3 is minus 0.5. And then I also introduce a bias term which is 2. Very simply, the output of the neuron is exactly what we discussed. The first input multiplied by the first weight, plus the second input multiplied by the second weight, plus the third input multiplied by the third weight, and then we add a bias term towards the end. That gives us our output. Remember that the indexing in Python starts from 0. So when I say inputs of 0, it will take the first element of this list. When I say inputs of 1, it will take the second element of this list. And when I say inputs of 2, it will take the third element of this list. So let me run this command, and here you can see the output is printed. The output is 2.3, which basically sums up the input into weights plus bias. You can think of the weights as assigning importance to the inputs. If the weight is very high, it's indicative that that particular input is very important. So coding a neuron is as simple as this. Great. So you have now coded your first neuron with three inputs. Let's say I want to increase the inputs to 4, which is something like as shown in the figure. Instead of three inputs, now I have 4: x1, x2, x3, and x4. Remember, when a neuron receives 4 inputs, it should also have 4 weights associated. One weight will be associated with each input. So then the weights become W1, W2, W3, W4, but the bias term remains only 1. That does not increase with the number of inputs. So then the output of this neuron is x1w1 plus x2w2 plus x3w3 plus x4w4 plus b. Okay. In the code, it looks exactly similar to what we had written previously. We first write down the inputs as a list, which are 4 inputs now. We write down the weights as a list, which are 4 weights, and we write down the bias term. And the output is the weighted summation of the inputs plus the bias. So what has been written here is just inputs of 0 into weights of 0, and similarly till the fourth input and the fourth weight, and then we add the bias term towards the end. Do not forget to add the bias because that is a very important function of the neuron. So let me run this. So now we have the output of a neuron with 4 inputs. I hope you are following with me up till now. We have represented the inputs as a list, the weights as a list. Then we do a summation which multiplies the inputs by the weights, and then we add a bias term. Very simple, no involvement of matrices up till now. Okay. Now we will come to the next part of the neural network architecture. So we finished this part, neuron with 3 inputs, and we finished coding the second part, which is neuron with 4 inputs. Now let's come to the third part, which is a layer of neurons. So this is where things start getting a bit tricky, because the main power of a neural network comes from arranging the neurons together into layers. So when you arrange a bunch of neurons together, it looks something like this. So let's say now we have an example where we have 4 inputs: x1, x2, x3, and x4, and we have 3 neurons which have been shown in the pink color here. So this is the first neuron, this is the second neuron, and this is the third neuron. Now, if you think about what I said, every neuron, if a neuron has 4 inputs coming to it, it should have 4 weights. So this first neuron should have 4 weights and a bias term. This second neuron should have 4 weights and a bias term. And this third neuron should have 4 weights and the bias term. So let's look at the first neuron initially. The weights coming into it from inputs x1, x2, x3, and x4 are represented by W11, W12, W13, and W14. So the first index here, 1, represents the first neuron. Similarly, let's look at the second neuron. The inputs coming to it are represented in purple. So it has 4 inputs coming to it, and so it will have 4 weights: W21, W22, W23, and W24, and a bias term B2. And now let's look at the third neuron. It has 4 weights again: W31, W31, W32, W33, and W34, and it has a bias term which is B3. Based on the inputs which and the weights coming to each neuron, it will have an output exactly like what we had seen before. So the output of the first neuron will be W11 into x1 plus W12 into x2 plus W13 into x3 plus W14 into x4 plus B1. And similarly, neurons 2 and neurons 3 will have their own output. Okay. So now we are going to code this in Python. So what is the input which you will need? You will need the input values x1, x2, x3, x4. You will need the weight values associated with all neurons. So you'll need four weight values for the first neuron, four weight values for the second neuron, and four weight values for the third neuron. And you will need a bias term for each neuron. So these are the things which you will need, and based on that, we can predict the output. So let us look at how to implement that in code. So as I mentioned, these are the four inputs. Again, it has been represented as a list. Okay. The one thing which I want to show you is how the weights have been represented here. So remember that every neuron will have four weights coming into it, right? So these four weights are the four weights which are coming into the first neuron, which is W11, W12, W13, and W14. These four weights are the four weights shown in purple, which are coming into the second neuron. And these four weights are the four weights represented in blue, which are coming in the third neuron. So initially, since there was only one set of weights, since there was only one neuron, we just represented it as a list, right? But now, since every neuron has its own set of weight, we represent this as a list of lists. So within this one big list, there are actually three lists. This is the first list, this is the second list, and this is the third list. Each list consists of the weights associated with that particular neuron. And then, as I said, every neuron will have bias terms associated with it, right? So that also can be maintained as a list. So B1 is equal to 2, B2 is equal to 3, and B3 is equal to zero point 0.5. Okay. Now I want to maintain the outputs. Remember, there will be three outputs, one coming from each neuron. So I'll maintain the outputs as a list. The first element of this list will be W11x1 plus W12x2 plus W13x3 plus W14x4 plus B1. So this is the first element of that list. So I have constructed an outputs list here whose first element is uh, this is x1 and weights 1 of 0, which means we are actually looking at uh, the first element. So let me actually deconstruct this further. Let me define weights 1. So weights 1 is weights 0. So this will give me the weights with associated with the first neuron. So here what I'm doing, I'm indexing the zeroth element of this list of lists. So this will give me the first list. Similarly, weights 2 will be weights and the first element of this, the second element of this list. And weights 3 will be denoted by the third element of this weights list of list. So this is how weights 1, weights 2, and weights 3 are defined. So weights 1, let me comment this. This is the list of weights associated with the first neuron. These are the list of weights associated with the second neuron, and these are the list of weights which are associated with the third neuron. Okay, and then the bias term has been represented over here, where bias 1 is 2, bias 2 is 3, and bias 3 is zero point 0.5. So let me run this now. So this has been run, which is working fine. So let me now show you how the outputs is constructed. So the output will be a list with three elements. The first element is W1. So now we look at, so for the first element, we need to look at the first neuron. And these are the list of weights associated with first neuron. So then we need to find the first element of this list, multiply it with the first input, Find the second element of this list, multiply with the second input. Find the third element of this list and multiply with the third input. And find the fourth element of this list and multiply with the fourth input. And then add the bias. Remember that all we are doing is just w11x1 plus w12x2 dot 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 up till w14 into x4. So what has been collected over here is w11, w12, w13, and w14. Similarly, what has been collected over here is W21, W22, W23, and W24. And what has been collected over here in the third output is W31, W32, W33, and W34. So now it will be very easy for you to understand how the first element of the output is constructed. Similarly, for the second element of the output, we need this summation. That's why we look at weights 2, and then we multiply each element of the weights 2 with the input and add the bias. Similarly, for the third element of the outputs, we have to look at this third neuron and the weights associated with it. So what we do is we take the weights associated with the third neuron, which is in weights 3, and then we multiply all of its element with the corresponding inputs, and we add bias for all of these. Now let me run this, and here you can see that now we have obtained three outputs. So the output of the first layer which we have obtained is 4.8. The output of the second, or the output of the first neuron is 4.8. The output of the second neuron is 1.21, and the output of the third neuron is 2.385. So the output of the second neuron is 1.21, and the output of the third neuron is 2.385. That's it. You have now coded your first layer of neurons. It's as simple as that. So I want to just show you an efficient way for coding. Right now, what we have actually done is that we have just written this summation, right, for every single neuron. But what if there are 50 neurons here? We cannot write this summation 50 times, right? And that's why it's better to use loops. So that's why now we are at a section where we are going to look at how to use loops for better and easier coding. So if you look at this loop which I have written, um, the outer loop sums over each weights and biases associated with each neuron. So all we are doing here is that in the outer loop, first we fix the neuron. So let's say we fix this neuron. So when we are looping in this outer loop, we look at one neuron and then we take its weight and its bias. Okay, and then what we do then, so when we fix this neuron, we take its weight and its bias, and then we multiply it with the input. That's it. So in the inner loop, what is done is that the inputs and the weights are considered, and then we just do this summation. We multiply the input with the weight values. So basically, we multiply W11 with x1, W12 with x2, W13 with x3, W14 with x4. That's what's happening in this inner loop. So what's happening over here is that we are just doing W11 into x1 plus W12 into x2 plus W13 into x3 plus W14 into x4. And what is happening over here is that then we come out of the inner loop and then we just add a bias. So this is plus B1, and that's it. So then we have computed this for the first neuron, and then we add it to this output list as the first element. So this will come here right now. Then we go to the outer loop again, and after the first neuron is completed, we move to the second neuron. And when we move to the second neuron, then again we come to the inner loop, and then this thing, when we come to this point for the second time, it will be w21 into x1 plus w22 into x2 plus w23 into x3 plus w24 into x4. And then when we add the bias term, it will look like this. plus b2, and then this output will be added as the or appended to the output list. So the output list initially was empty, then we added the first neuron's output, then we added the second neuron's output, or rather appended the output. After we are done for the second neuron, then we move to the third neuron, and now we go to the outer loop, move to the third neuron, collect its weight and bias, and then multiply it with the input. So then when we come to the inner loop, it will be w31 into x1 plus w32 into x2 plus w33 into x3 plus w34 into x4. And then when we come to the output of the neuron, it will be this summation plus b3, and then this output will be appended as the last element of the output list. So we get this kind of an output list. And here I have used different set of weights, so let me again try to use the same weights here as what we have done here. So now these are the weights, and let me do this as the bias, and my input, let me keep it the same as what I had before, and let me run this. So now you can see that the output is 4.8, 1.21, and 2.385. This is exactly the same as the output which we got in the earlier code, where we just wrote down everything without writing the loop. Do you see the advantage of writing this loop? Now we are in a situation where no matter how many inputs you have, no matter how many weights you have, you just specify the inputs, the weights, the biases here, and this same code will run, because this code has been written such that it's independent of the number of neurons, number of weights, etc., as long as they have been specified here. So it will be much easier to scale as the neural network goes increasing to bigger and bigger and bigger architectures. So one purpose of this series is, along with understanding neural networks, you also need to develop an understanding of coding in Python. So try to use these lectures to also brush up this understanding. Initially, I did plan to cover NumPy and how to implement neurons and layers in NumPy, but then the lecture length will become large. So I'll stop here for today's lecture. In the next lecture, I'll be showing you why people use NumPy and how to use NumPy to code the neurons, to code the layers. And then we'll also be looking at batches of data. Currently, only one input is coming, right? But what if multiple inputs are coming to the neural network? Let's look at that in the next lecture. So, thank you so much, everyone. I hope you got a lot of value from this lecture. There will be many more parts in the upcoming lectures, because we have a lot of different things to cover, as has been mentioned in this index over here. And we'll be doing everything from scratch, like what I showed you in today's lecture. I'll not assume that you know anything. The places where we need to write down things, I'll write it down, because one thing I've learned about matrices is that unless you write it down, you don't really understand the dimensions. Thank you so much, everyone, and I look forward to seeing you in the next video.